So, good afternoon, everybody. Welcome to my talk, Reactive Android, RxJava, and beyond. A little background about myself. I am based in Amsterdam, where I work both as an Android engineer and a Scala engineer. And I mostly use Scala for back-end applications. And those are a few of the companies that I worked for over the past few years, either as a freelancer or as an employee, or some of the actually open source projects. And some time ago, I got so fascinated by this reactive programming concept that I ended up starting my own Reactive Amsterdam meetup. And these reactive principles are cross-technology, cross-domain. So really, basically, I started this meetup to explore the concept in all of its forms. And if we start from the vocabulary, what does reactive mean? It tells us that it's an adjective and is tending to act in response to an agent or influence. Now, upon mentioning this word to people in technology, though, I noticed that there is quite some reactive confusion about it. Some quotes that I got lately are, I was thinking of using Node.js, but maybe I can build it with reactive. Thanks for running a meetup about React.js. So there's two main observations we can take here. The first one is that the concept of reactive has common basis but slightly different meanings in each domain. And the second one is that most of us think that reactive and React.js are the same thing. So from my perspective about running this reactive meetup, I focused on the two tech domains that I know best, which are Android with front-end in Android and back-end in Scala. And I investigated a little bit, what do people think that being reactive means? And for Android, it really comes down to using RxJava. Later, we will also see how people see it from a back-end perspective, and we will see if we can bridge some gap there. But let's start with an introduction to Reactive Java. Oh, by the way, RxJava, Reactive Java are like sort of interchangeable, so I'll use both of them, and they mean the same thing. So Reactive Java is part of the Reactive X family, which is a set of open source libraries that help us work with asynchronous programming and observable streams. So this concept of streams is really key, and we'll see later a bit more about it. And so yes, let's see what this all means in some detail. So mobile engineering is hard, and there are high expectations. And with this respect, Reactive Java is cool because it makes it super easy to switch between threads, lets us deal with data as a stream, and brings us some degree of functional programming. And before we dive a little bit into Reactive Java, let's see another premise, is that Reactive Java goes hand in hand with the Lambdas from Java 8. So as an example, there you have the implementation of an interface, func1, and there's a method there called call that takes a string as an input, and then it outputs its length. So it's an integer. Now using lambdas, this could be simplified as this. So you have string s, that's the input, and then the body is executed, and it returns the length of the string. And in this case, because the body is only one line, we can further simplify it like this. So really, really a lot less code. And bear in mind for Android that Android APIs prior than N, which is still in preview, they cannot use Java 8 features. So if you want to use lambdas, for instance, in your Android app before Android N, you have to use this Retro Lambda plugin. But it's very easy to set up. So if we go a little bit into some examples, this is a class that we will use for examples. So a simple cat class. Has a get color method, fetch picture, other simple things like that. And now, imagine that we have a collection of cats, so my cats. The observable class in RxJava library has a static method called from that takes as input a collection, and it will emit all the items in the collection one by one. And so this is called observable, and it's factually a stream. So all the items in the collection one by one. In order to do something with these items, we need to subscribe to the observable using the subscribe function. And this function will take as a parameter the implementation of an interface, which takes then a cat as an input, and then you can do something with it. Now, in this case, I'm just logging that we got a cat. And see, you see that this is a Lambda. Imagine if I had to use, the whole old Java syntax. It would be like take probably the entire wall. Usually, this stuff is chained. So what you usually see is this, which is also a lot easier to read. Now, at this point, you might be wondering, so if I want to do something with each item of that collection, with each cat, I can just do it with a plain old for loop. Now, the beauty of Reactive Java in this is that it allows you to manipulate the stream as it goes without breaking it. So, for instance, in this case, there are many, many operators in this library that let you manipulate the stream. In this case, we're using a map. It's like a functional operator that what basically does, it lets you, it takes one type of object in input, and then it lets you output another object, another type of object, after maybe you've manipulated it. In this case, the stream passes on a cat, but we will return after the map a color, get color. And so when we subscribe to this observable, we will deal with color objects. And then we log got color. And there are many, many operators like this. Just another couple of examples. We can use distinct, which will make sure that that two duplicate cats don't make into the stream. And then delay will make sure that each item, each cat is emitted with a 2-second delay. Then filter, it will only propagate in the stream cats that satisfy that condition. So in this case, that are white. And there's many, many operators like this. A couple of words about the subscribe interface. So actually, the observable object is a typed object, and the subscribe function can take up to 3 optional implementation of interfaces, where the first one on next is what we have seen so far. So it's the next item T in the stream. Then, if something goes wrong along the way in the stream, we will get an on-error call with a throwable. And then onComplete is just really a signal that the stream has reached its end. So in real life, it could look like this. At the end, we're just printing that the stream was done. All right, and then because we are dealing with streams that are potentially endless, at some point you might want to unsubscribe from this stream. And what actually happens is that subscribe method at the end, it returns a subscription object. So if you hold a reference to that, then later at some point you can unsubscribe from that observable, and you will stop receiving objects. Now, earlier we mentioned that RxJava makes threading easy. So let's see how that works. Imagine that you have this stream where with this observable, you take first each cat, and you fetch a picture of it. So it's a network operation. So it's a heavy operation. You don't know how long it's going to take. Then after that, the following map will receive the picture in input, and then you want to apply a filter on it, which also it's a heavy operation. And then at the end, in the subscribe, when we receive the filtered picture, we want to display it. So load it into our image view, for instance, in Android. So what you want to do really is take those 2 map operations and put them on some other thread that is not the main thread. And it's quite easy. Using these operators subscribe on, we can really tell this observable to execute the following stream on a different thread. a new thread in this case. Schedulers is also an object in the library. And then at the end, when we want to have those results on the main thread, we can use observe on, and then under the scheduler's main thread. So, and that, calling that operator makes sure that everything that follows happens on the main thread. That's all we have to do. Very easy. There are many ways of creating observables. What we've used so far is with collections, but there is also, for instance, this just will take one single item and then complete. Timer takes one item and emits it only after a certain delay. And there's many, many others. You can obviously look into the library documentation, and you can also create your own, which is not very, very easy. It can be a bit difficult, but it's a lot of fun. So I encourage you to try that. Now, to do a real life example, I decided to take the Meetup streaming API. So that URL is actually a public URL. And if you query it from curl, let's say from command line, it outputs an endless stream of responses to event. So RSVP, so people that say yes or no, basically. And I have a little video here. I hope it plays. Oh, yeah, see, that's curl. So when we call this, the response contains, a lot of garbage, it looks like, but it's really just responses to events. So basically, yes or no tells you which user was that and which event, which location. Now, if we want to use this in an Android app, we can set up our interface using Retrofit. And Retrofit is really cool because in this sense, it allows us to use that streaming annotation, which lets us access the raw body of the response, of the HTTP response, and also lets us have a handle on this response as an observable. So what we do later in our code is to set up a stream, an observable that looks like this. We get the response body item, and look at that operator, it's FlatMap. It's similar to map, but instead of taking an input of one type and returning a different type, it returns an observable of a different type. So that events function that you see in the FlatMap, what it does, basically, it takes the body of the HTTP response, and in its internals, will basically listen to each chunk that comes through the stream, take that chunk, and re-emit it again in the stream as a string. So this following map call will take that string and, well, convert it from a string into a RSVP class using JSON. And then our subscribe at the end, so we'll get a stream of RSVP objects. At which point I just log something. And in presentations it's bad to have live demos, so I made a little video. I'm going to click on that app, say listen to events, and events will start streaming in. Yes, yes, no. And then when we click on enough there, it will unsubscribe. And so we stop getting data from this stream. If you're interested, this code is on GitHub, and you're more than welcome to contribute, have fun with it. See how the events function worked internally. I didn't put it here for brevity. All right, so back to square one. This was an overview of Reactive Java, which is more or less what is widely considered all there is to be reactive in Android. But how about the point of view of a backend developer? So in order to understand this point of view, we need to go a little bit through the evolution of server application and user expectations over the last decade. And so if we talk about servers, web services maybe used to have servers in the orders of tens. Nowadays, there's no limit really to how many you can have. Response time was expected to be about seconds, now it's milliseconds. Offline maintenance, maybe a web service was offline for hours, but nowadays it's just expected to be always online. So your user or services that use your service expected to be always there. Data amount, we went from gigs to petabytes. and maybe more. Machines were single core with little distribution, but nowadays they must be able to work across asynchronous boundaries. So maybe both geographically, because they're in different places, but even within the same machine, there are many cores and different threads. They need to interact with each other. Finally, the kind of data, maybe 10 years ago, was just a classic standard HTTP request response done, but now we're dealing with streams more and more, potentially endless. So this evolution has come in response to the evolution of the usage of internet, actually. So what we can see is that as the user base grew and also services like Facebook or Twitter, all these things, they grew in usage, many frameworks and tooling have come along to help us achieve all these things. And we'll be focusing a little bit now on this Reactive Manifesto that came out in about 2013. The Reactive Manifesto is not really a tool. It's more of a design guideline, design principles on how to achieve a reactive system. And what it does, it starts with defining a few reactive traits, a few qualities that your system should have in order to be reactive. And what are these traits? So a reactive computer system must react to its users, so be responsive, react to failure and stay available, that is resilient, react to varying load conditions, so be elastic, and then its components must react to inputs. So this last one, we'll go through these 4 traits in a little more detail, but this last one is message-driven, is a little odd. We'll see where it fits. And all these traits are all interconnected. So they work together, and they're usually shown as this graph, which I personally find very incomprehensible and not really explaining anything. So let's go through these traits one by one. Responsive. A reactive system responds to inputs and usage from its user. And bear in mind that here a user could be, yes, a human who visits a website, but also a client, generic, which makes a request to a server. It could be a consumer which contacts a provider. Basically just anything requesting a service from something else in the very generic terms. Then elastic. So being elastic means that your system is able to scale on demand to react to varying load. So what happens is, in many, many systems, the amount of load of traffic changes over days, maybe weeks or part of the year. Think about an online store that has Christmas sales or Black Friday sales. Then it's a peak of traffic. A banking system might have payday. So, and such things like this. And elasticity means that you're able to use just the right amount of resources. So it's important to scale out when you need more resources, but it's also important to scale back in when those resources are not needed anymore, because those resources cost money. So you need to be able to use just the right amount. And elasticity nowadays, of course, relies on distribution. So you want to be able to add a resource in an independent fashion from the previous ones, and that should just work no matter where it is. And this distribution also help ensure replication in case of failure. So if one of your nodes goes down, then you will have another one. So you start seeing how this is all interconnected, these traits. The next one, resilience. This is really important because it basically doesn't matter how great your application is if it crashes and doesn't work. So what we want to have is resilience in our system, which is defined as the ability of something to spring back into shape after a failure. So what we're talking here is that we don't want to, it's different than fault tolerance, because fault tolerance is when you get hit, but you keep going. No matter, maybe your internal your state is mess, but you get hit by errors and failures and keep going. So I guess it looks like this. But we don't want that. We want to heal fully. So being hit and then restore to a fresh state. And that's resilience. And it goes beyond fault tolerance. We just want to have a fresh start. And then this last odd trait, the message-driven trait, is about asynchronous messaging. Because one thing that we will encounter when designing this system is that we'll focus on messages. Because if only messages are exchanged between components, you have two components, they only talk to each other with messages, then when you have achieved that, asynchronously, of course, when you have achieved that, you have achieved total separation, which helps with error containment. So separation between components, error containment. That means that if this component fails for some reason, crashes, then this other guy is completely independent and so is not affected by it. And this is called error containment. You don't want chain failures in your system. And so in this case, instead of focusing on class diagrams or interface definition, what we focus on is the protocol that defines how components talk to each other, who says what and when. And then there's also another thing, that these messages, I think that they help to map your domain in a way that is a little bit closer to reality. Because, in the real world, we don't read each other's brain, right? We communicate, we send messages to each other. Well, we don't read in each other's brain yet, I think, at least. So this maybe helps us map our domain into terms that are more closer to reality. So after seeing these traits a little bit more, we can go back to this useless diagram and substitute it with a better one, which I think is this one. So on top, the values that the reactive systems want to achieve, so responsive, maintainable, extensible, and the means by which we achieve that is being elastic and resilient. And these qualities are enabled by a message-driven system. Another one thing to talk about is when we mention reactive programming, it's always about reactive functional programming. And so why is that? Well, the answer, the most important answer is there, that this functional programming is more supportive of reasoning about problems in a concurrent and parallelized applications, which is what modern applications are made of, basically. This paradigm encourages use of pure functions. So there are functions that, the idea is to minimize side effect. So when you minimize side effect, then all your state is contained somewhere. You don't have consequences on the outside world, which in turn helps the separations between components. Same idea here. Functional programming encourages immutability. So state mutation is, concealed as much as you can. It's limited to one single component, and state doesn't get passed around. So this again helps separation. And there are higher order functions. So that means that in functional programming, functions can be passed around as parameters. This is what we have seen earlier with lambdas, basically. That's the idea. And that helps reusability and composability of your system. Now, so we have seen these reactive traits. Now we're going to talk, the next step is what are the design patterns that help us achieve those principles. There are a few toolkits and frameworks to help us implement these patterns. And I would say the most mature one, I think, is Akka, which is a framework that runs on the Java virtual machine, and APIs are available for both Java and Scala. So what are these patterns? The first one, very simple component pattern. One component should do only one thing, but do it in full. The aim is to maximize cohesion and minimize coupling between components. It's basically what we have been saying so far. And the way that Akka tries to implement this is by basing applications on the actor model. So what is an actor? An actor is an isolated component that contains state, behavior, a mailbox to receive and send messages, so actors can talk to each other. And each actor contains some behavior logic that it's only his, it's not shared with anybody. And very importantly, actors have supervisor. We'll see later what a supervisor is, just in a second, but it's really, really crucial to achieve resilience and error containment. This leads us to our second design pattern, which is called let it crash. It says, prefer a full component restart to complex internal failure handling. So it sounds a bit counterintuitive, but let's see what it means. We have to accept the fact that failure conditions will occur at some point. They might be rare and hard to reproduce. And that sometimes it is much better to start clean than to try and recover from a messy internal state, because that might be expensive and difficult. And of course, you all remember the king of bad failure handling, our old friend, the blue screen of death. So to avoid that, what do we need in practice? Again, components should be isolated and no sharing of their internal state. And then these components, they can have a supervisor and delegate to the supervisor some of all the error handling that we need to do. Because at that point, the supervisor can transparently deal with the error and, if needed, restart the component fresh. So that's resilient, like shape back into a fresh state. And that can be done transparently for other components. And this is really what message passing architectures enable. And so it enforces state confinement, error containment, and transparency. How does this work? A little example here. You have these two actors, and that's the supervisor. So you would have actor 1 sends a message to actor 2 requesting some service. And then this is totally asynchronous. So after that message has been sent, they're not coupled in any way. And so actor 2 can do his work independently. But then as actor 2 works, an error occurs somewhere in the process. So at this point, what actor 2 can do is it can scale up the error and tell its supervisor about the exception or whatever error it was. This enabled the supervisor to understand what the problem is, so maybe fix or restart entirely the actor, which at this point is again in a clean state, tries to do his work again, and finally sends message back to the actor 1 with the result of his work. There is a little analogy that I like to show, maybe to better understand this again in real life. Imagine a developer that wants coffee. I think it's a very, very common situation. So imagine you go to the coffee machine, and that DE doesn't mean Germany at all. It's Douwe Egberts is a very common, very famous Dutch coffee machine brand. So this is an old machine, as you can see, it's big. And it only accepts exact change. So, scenario 1. This user has inserted the wrong amount of coins. So at this point, the machine prompts, hey, error to the user, you inserted the wrong amount of coins. And then hopefully also gives you the coins back. So that's a legitimate error. But how about this, scenario number 2? The machine is out of coffee beans. At this point, this is what we call a failure, because it's not a user mistake. It's something that it's an internal failure of the coffee machine, independent from the user. Now imagine if, in reality, this machine could send a message to the supervisor, and then the supervisor could decide to do something about it, and then, for instance, in this case, a coffee beans injection, and then the user could have his warm cup of tea. And the user didn't realize about what was going on with the supervisor and all. He just maybe waited a little longer, but then got his cup of tea, of coffee. So this is the whole principle about error containment and transparency for your user. Someone that has embraced this pattern very well is Netflix with their Chaos Monkey. So maybe you've heard about this. In short, Netflix architecture is obviously very, very big. They have a lot of servers and especially a lot of Amazon Web Services instances running. And what they do is they have this program that randomly kills instances on their infrastructure to ensure that the system keeps going, even if one of the nodes has been killed. And so what they want to check is that there is no failure cascading through other nodes, but then the whole system keeps working. Maybe the load is a little bit redistributed across the other nodes, something like that. But in general, it should be a failure should be transparent for the rest. So at this point, back to our slide here. What do people think that being reactive means? Now we can see that when we talk about reactive to a backend developer, he will think about elasticity, asynchronicity, resilience, supervision, message passing, set encapsulation, streams, back pressure that we didn't even have time to mention, and even other things. And so the question that I am left with here is, can we apply some of the Reactive Manifesto principles to our Android development? Can we establish a vocabulary of terms that is common to everybody? Can we unify these reactive efforts? Now, I reckon you guys could potentially be more confused now than when we started. That is possibly a good thing. But let's say we want to try and do a very superficial, we don't have a lot of time left, I'm afraid, very superficial comparison. How would these reactive traits apply in Android? Responsive, well, you should execute as much as possible asynchronously. We kind of know that already. Elastic, okay, it doesn't really apply, as there's only one app in your hands. But resilient, maybe it's an idea to delegate risky stuff to services or intent services or somehow isolated components. And then message passing, what can we do? Communication, yeah, asynchronous communication via result receiver. Maybe use some event bus. So I don't know, this is really just a superficial, the first thing that comes to mind. But I'm sure we can take this a lot further. And I want to keep working on this. So if you think that this is also a thing that is worthwhile doing, you're more than welcome to reach out to me, contribute, and with ideas. This is a list of resources that I used. If you want to dive deeper into this concept, reactive, what does it mean? Learn to use Reactive Java, really a cool thing. And that's it for today. Thank you. I think we have maybe some time for a couple of questions, if there's any. Oh. About back pressure. Yeah. So back pressure was this thing that we didn't have time to cover. It's basically the idea that if you have, the question is what do you think about back pressure, if you guys didn't hear it. So back pressure is when you have a source of data that is emitting data, and then you are here, you're listening to this data. But at some point, this data maybe starts coming too fast. It's maybe more than the capacity that you have to handle data. So at some point, you risk to have a buffer overflow or some other error happening. And so what you can do is you tell to the source, say, slow down, take it easy, you're swamping me. And actually, Reactive Java has a operator to manage back pressure. So if whoever subscribes to the observable has the capacity of telling back to the source, hey, slow down, then you can tell to the observable like maybe how many items it should keep in the buffer and stuff like that. And even within an Android app, I think it is useful. I have used it in one case where I was trying to insert stuff in a database asynchronously, but the content provider wasn't fast enough, And so I applied some back pressure. So it can be done. To be responsive. Yeah, well, like in an Android app, what you care is really mostly being responsive to the user, I suppose. And so, you know, all these things happen in a background thread anyway, and the user doesn't see it in this Android case. But now, if we want to open a discussion about back pressure, that's maybe a little too big for this place. Yeah? Go ahead. So, the first one oh, yes. Right, so the question is, first is what happens when a supervisor of your actor fails itself? There is, in akka, there is a hierarchy of supervisors. So your supervisor is actually an actor itself. So he also has a supervisor, that's the thing. And then at the very core, at the top of this hierarchy, there is a you could call it like a pseudo sort of root supervisor, which as an ultimate solution kills everything. So also kills supervisors and everything that comes below. So what happens then is that errors are escalated all the way up, and so if your supervisor cannot deal with it, it will escalate it to its supervisor and so forth until God, basically, that kills everyone. And then Vertex. Vertex is another one of these toolings. It's funny, are you a member of Reactive Amsterdam meetup? Oh, you could come. We had a talk about Vertex, when was it, maybe 2 or 3 weeks ago? It was really interesting. And, Vertex, on its side, with respect to akka, has that it's more polyglot. Like, you can use Vertex a bit everywhere. And, I would say they achieve the same... They try and solve the same thing of making things more reactive and asynchronous and dealing with the back pressure and these things. I have never used it, but from the presentation I saw, it was really cool. Sure. Any other questions? Right, it seems we're done here. Oh, no. Oh, yeah. yeah, good point. A bit of shameless promotion is good. Tomorrow night, there is a meetup about reactive programming in iOS. So especially if you use Swift, that might be your cup of tea. And here in Amsterdam. And yeah, we're hosted by the Uber offices here. They're pretty cool, so might be worth checking out if you can still handle it after a full day of conference. Anyway, thanks guys for attending.